Hello, I'm Kevin. I'm a founding engineer at Eventual, and today I'd like to talk to you guys about some of the lessons that we've learned from building Iceberg capabilities into Daft, which is our distributed query engine. Some things about me. I'm Kevin. I work on Daft. My work touches various aspects of Daft, including the query optimizer, LLM batch inference workflows, as well as catalog integrations. Notably, I shipped Daft's Iceberg writer, including the capability to do partitioned writes. So here's an overview of what I'm going to talk about in this talk. First, I'm going to give an introduction to what Daft is. Then we'll talk about how Daft integrates with Iceberg. We'll go over some challenges that we faced building Iceberg capabilities into Daft, including a few specific examples. And then finally, I'll go over a proposal for what a future library could look like that could solve some of these challenges. So Daft is a Rust-based distributed query engine. It's made for various workloads, including analytics, data engineering, and multimodal AI ML workflows. It has first-class support for both Python as a data frame library, as well as SQL, and it has great integrations with various table formats, data sources, including, of course, Iceberg. So the landscape of Iceberg sort of looks like this today if you want to query Iceberg. On one side is the engines that can do distributed querying, things like Spark and Trino and ClickHouse. They allow you to do querying of Iceberg tables at scale, allow you to do a lot of great sort of analytics workflows with all of the data that you have. On the other hand are these Python native experiences provided by libraries such as pandas and polars. They give you great workflows for interacting with your Iceberg data using Python and doing a lot of these AI and ML things that are often in the data science and AI landscape in the Python ecosystem and allow you to use a lot of the Python libraries that you love. Daft is in a unique position where it can leverage large-scale data and do a lot of great analytics by giving you the capabilities to do distributed querying processing, but it also has a lot of great Python native features that allow you to do all of the various AI and multimodal stuff that you want to do if you are a data scientist. Okay, so this is a little blurry, but I think we can piece it out. Using Daft in Iceberg is pretty simple. Daft integrates with PyIceberg to do reads and writes. So here's an example where we get a SQL catalog using PyIceberg, and you can pass a PyIceberg table directly into Daft.readIceberg to read it, do your various data frame operations, and then write the table, write a PyIceberg table out using dataframe.writeIceberg. So that's a quick example of how you can use Daft. Using PyIceberg, let's get a little bit into the internals. When a local engine, one such as Pandas, uses PyIceberg, PyIceberg touches three different things. The catalog to get things like the table, location, credentials, and basic information to access the table data and metadata. And then you have the table metadata as well as the table data. PyIceberg handles interactions with all of these, and so it provides a good interface along with the compute that's needed to do things like partitioning and deletions. And when a query engine wants some data from PyIceberg or wants to write some data out to Iceberg, it simply sends and receives data as fully materialized PyArrow tables. So the interface is pretty straightforward. However, PyIceberg's data interface is a single machine interface. It runs all the I/O and compute on a single machine. It does not fit into Daft's distributed model. You can't scale it out so easily. So instead, we implement our own distributed compute and I/O. So in this diagram here, instead of taking the data itself, we take from PyIceberg the info about the table, and then we distribute the work out to the cluster, which actually downloads the data or uploads the data. And we rely on PyIceberg for things such as a lot of the Iceberg-specific logic, metadata reads and writes, as well as interactions with the catalogs. So during our evaluation and implementation of our Iceberg implementations, we faced a few challenges when using both PyIceberg as well as the Rust library for Iceberg, Iceberg Rust. The main two that we faced are incomplete implementations of the Iceberg spec as well as different levels of abstraction that are desired. So in terms of implementation, there's really good progress being made on both libraries, but the reality is like Iceberg on the Java side, it's the bleeding edge, implements the entire spec, whereas Python and Rust always have to basically keep playing catch up. On the abstraction side, most engines are pretty happy with using the sort of high-level data interface using things like PyArrow, whereas for us, a lower-level API would be better suited. So let me give a few examples of that, actually. So the first example is table writes. PyIceberg does support table writes, but if you are going to use it for table writes, it assumes that your data is in one PyArrow table. If you're a distributed engine, you have a few options. The first one is you collect all of your data into Arrow. And the result of that is you are limiting yourself to writing only the size of, like the largest table that you can write is the memory of one single node on your cluster. And you can't take advantage of all the I/O and compute that your cluster enables. The alternative is to re-implement large parts of the Iceberg transactional logic that PyIceberg does. And that's the one that we chose to do. We can't use, unfortunately, the nice abstractions provided by PyIceberg anymore if we do this, but we can patch in, because we're re-implementing a lot of this, our distributed write functionality. So here's an example of one of the abstractions that we can no longer really use. This one is the append method of PyIceberg that we had to, the logic for choosing it, we had to port to the Daft side. And it's something that is only PyIceberg specific and doesn't really have to do with anything on our end of whether or not, there's no decision that it needs to be made on the Daft side. However, because we have to sort of tear apart this abstraction, we have to include stuff like this into our code base. Instead, we would prefer to not have to think about any of sort of how PyIceberg does the append method at all. Another example is partition writes. PyIceberg does support partition writes since 0.7, and we quickly added support for that, and we were very happy to have that. But PyIceberg, for some reason, bucket and truncation transforms for partitioning are not supported. Why? This seems like a very weird thing to me, right? Because we have our temporal transforms, they work great. The reason is, at least for bucket partitioning, is that PyIceberg handles the compute for these partitioning keys using PyArrow. It does its own compute for that. Bucket transforms, as you can see from the screenshot that I took of the PyIceberg spec, requires a specialized bucketing function that requires the murmur3 hash, among other things. And that is just not implemented in PyArrow, so there is no performant way to actually do this in PyIceberg, so they chose not to implement it. So our solution to that, to bring this functionality to Daft, is to build our own vectorized partition transforms, including bucketing and truncation. But we had to re-implement a lot of the logic for partitioning to be able to insert that into our Iceberg writes. So the result is that Daft technically does support a larger subset of the Iceberg spec than PyIceberg, which we find pretty interesting. However, this is not the ideal. The ideal would be that we could easily plug in our own compute if we wanted to without needing to peel away all of these abstractions about the partitioning logic that PyIceberg sort of hides from other libraries. Okay, so looking ahead, I'm going to give a few proposals about how to solve these problems. The first challenge that I listed before was that there's incomplete implementations of the Iceberg spec. The current state is that there's multiple independent implementations Iceberg, Iceberg Rust. That covers some different subsets of the spec. An alternative to that would be to build a single low-level API with all of the core Iceberg logic that's easy to basically cover the entire spec, and then provide various bindings and high-level APIs that can be used for different languages as well as different memory formats, such as like Arrow. The other challenge, should say challenge number 2, is that there were different levels of abstraction that were desired. Sorry about the wrong title here. The current state is that the Iceberg spec itself is unopinionated about how you do your compute, your I/O, and your in-memory representation, but the libraries themselves are, so that you can have some easy-to-use abstractions for these libraries. And the alternative to that, our proposal is to essentially separate out the logic of the core Iceberg functionality from the other layers of compute, I/O, and memory representation, so that query engines can access either the lower level, sort of close to spec APIs, or the higher level data interfaces. So what that looks like is this. You would have, again, your storage level stuff, your catalog, metadata, and data that you need to use. And there would be a Iceberg core library, say, that interfaces with catalog and metadata stuff. And then there would be various APIs that are more opinionated about the languages, about the in-memory formats, such as like a PyArrow table that pandas can use, or an Arrow RS table that Data Fusion can use, but also a library like Daft, who wants to do our own stuff, can directly interface with both the Iceberg core as well as the data itself. So taking a step back from that, this is what sort of the Iceberg ecosystem could look like. Divided into 4 general sections. The first one is the unified Iceberg kernel, which includes the core Iceberg logic that I was talking about, as well as the types, as well as the catalog clients. The second layer above that is the data layers, including storage clients, so reading and writing data to your storage providers, memory formats, such as Arrow or Daft's own memory format, as well as Iceberg-specific compute. And those are things that you can either choose to use or choose to implement yourself. And then on the third level is query engines, which actually interact with these data layers and in proxy these Iceberg kernels. And they have their own opinions about query planning and execution that I won't go into in this. But then finally, taking a step back from even that, what do users actually want? They want to actually use their data. And how do they do that? Well, the 2 interfaces that are generally provided are going to be data frames and SQL. So that's sort of the ecosystem and sort of different layers that we envision here at Daft. Okay, so some final words. We're very excited to see the growth of Iceberg. We've seen a lot of users use Iceberg on Daft and finding a lot of success in the past year. And we're very proud to be part of the Iceberg and Rust ecosystem. Shout out to all the contributors of Iceberg and Iceberg Rust. It's a great community-driven effort. I know some of you are out here. We're super grateful for your work, and we would all love to continue our collaboration. And finally, if you would like to try out Daft, you can do so by doing pip install get Daft. And also, as Chan Chen mentioned before, feel free to join our distributed Slack. Yeah.
Who has questions? Anyone have any questions? Oh, awesome.
Hello.
Hello.
What are you using Iceberg Rust for versus Iceberg?
So currently we do not use Iceberg Rust because it lacks certain functionalities on, I think primarily on the catalog support side, supporting things like glue, as well as on the writing side. But we hope to in the future be able to do that so that we don't have a Python dependency when we're doing things like running SQL.
You mentioned like this common layer, but this seems to be a little bit vague. And if we assume that the Iceberg will evolve, there will be like a new version of standard, there will be more features there. Every language would like to support it natively. So sometimes, but everybody likes C bindings for some reason. So do you have any more concrete proposal how this should look like?
Are you talking about like how to actually like specifics on the like the bindings level stuff?
how to build something that will be the good solution long term, that will both allow like evolving for next iteration of Iceberg, as well as support by many languages and not re-implementing catch-up games?
Yeah, it's a great question. It's something that definitely like needs to be figured out as it goes. I think like it's not something that you can like immediately know because of like the evolution of the ecosystem and the spec, right? But the sort of the general idea is like we would have something like C bindings for a core subset of Iceberg. There would be a lot of things such as like the metadata formats and stuff like that all baked into that core, so that it doesn't need to be implemented multiple times throughout the various libraries. And then these like other libraries, these other languages would have bindings for them that can be easily used by a sort of like another library on top of that that provides language-specific support for that kind of functionality. Does that answer your question? Cool.